So now we're going to have a look at our last distribution free test. Remember that we've already had a look at the sign test for single and paired data, the Wilcoxon rank sign test for single and paired data, and now we're going to have a look at the Wilcoxon rank sum test. So again, the Wilcoxon rank sum is a distribution free and non-parametric test. And if you're still confused with those meanings, please have a look back at the first sign test with single data video. For the difference between two sets of data, so this time we don't have a single and a paired, we just have two sets of data. And just to emphasise that we're not talking about paired data this time, so we're still talking about the same information, but this time it can be from two or one sources. So it's still going to be the same information, but it could be about two different things. It is also known as the Mann-Whitney-U test. Quite a lot of textbooks refer to it as the Mann-Whitney-U test. So if you see any textbooks with that, it is the same test that's being performed. One important difference is that as the data is not paired, there is no reason to have the same number of values in each set. And that's quite a big giveaway with this test. Not only is the data not paired, so there's nothing linking the values together, but also quite a lot of the time there's no need for the same number of values in each set. And it's the only hypothesis test that we've had a look at so far where you can have different sample sizes. So for both one and two-tailed tests, we're going to get our critical values from our formula booklet again. It's the last page in the formula booklet, so page 26. And this time we are limited to what significance levels we can use, as we only have tables for the one tail 5%, and the one tail 2.5%, the two tail 10%, and the two tail 5%. So it's going to be one of those four. So as you can see here, I've put snippets of the tables from the critical value booklet, and you can see here one tail test 5%, two tail test 10%, and the reason for that being similar way as it was described when we were talking about binomial and normal, that a two tail test you are splitting 5% below, 5% above, which is why it's a one-tail test for the 5%, and similarly here for the one-tail 2.5% and the two-tail 5%. So something else that is in the formula booklet is the formula that we need to use. So the formula that we're going to be using, this is for one-tail and two-tail tests, and again this is on page 26 in your formula booklet, is the U equals T minus N plus 1 over 2. And we are going to be using this in our hypothesis test. So I just wrote it at the top there, but it is on page 26 in your formula booklet, so you don't need to learn it. So that's in the formula booklet. So we're going to have a quick look at a one-tail test. So Julia has obtained two samples of grapefruit, one from supermarket A and another from supermarket B. So this is quite important, like I was saying before. Both of these are grapefruits. One of them is from supermarket A though, and the other is from supermarket B. So there's nothing linking this 164 to this 208 apart from the fact that they are both grapefruits. So the grapefruits are weighed on the same scales, and the recording of the weights is in the table here. And we're trying to investigate whether there is a significant evidence at a 5% significance level to believe that the grapefruits from supermarket A are smaller than those from supermarket B. Now again, as with all the other hypothesis tests apart from chi-squared, we can use symbols for this. So we're going to have H0, and again we are talking about the median. So we're looking at median A is equal to median B. So it's a little bit different this time. And then our H1 is going to be that median A, we want that to be smaller than median B. Now it's quite important that we define what these symbols mean. So median A is the population median weight of a grapefruit from supermarket A, and median B is the population median weight of a grapefruit from supermarket B. And that's really important that we make it clear what each of our symbols stands for. In this case, it's quite obvious. A is for A, B is for B, but it's still quite important that we are communicating what each one of those means. And this comes up quite a lot in A2 statistics, so it's a good idea to get used to it now, defining what our symbols mean. So then we are going to rank our data. Now this is different to how we have done ranking before, as we are going to rank all the data as one big set of data. So we're looking at both A and B, and the smallest number that we can see is 104. So that gets the rank of 1. So then looking at both A and B, the next smallest one is 116. Then the next smallest one is 118, so that gets the rank 3. It doesn't matter that that's in group B, we're ranking it all as one big set of data. Then the next smallest is 120, which will get the rank 4. The next smallest is 132, that's going to get the rank 5. The next smallest is 140, that's going to get the rank 6. The next smallest is 144, which gets the rank 7. The next smallest is 153, which gets the rank 8. Then 164, which gets the rank 9. Then 167, which gets the rank 10. Then 169, which gets the rank 11. 197 will get the rank 12. 208 will get the rank 13. 212 will get the rank 14, and 246 will get the rank 15. And just to double check, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 pieces of data, and I got up to rank 15. So then we need to add up the ranks separately. So now we're going to end up with a total for A and a total for B. So now we are going to add these ranks up separately. So for A, we had 9 plus 14 plus 5 plus 6 plus 2 plus 1 plus 10. And that gave us 47. Then we had 13 plus 15 plus 12 plus 8 plus 3 plus 11 plus 4 plus 7, which gives us 73. And in the same way as we could check with Wilcoxon sign rank test, we can check that we've added those up correctly. We had 15, so 15 times 16 divided by 2 gives us 120, and 47 plus 73 also gives us 120. So we've definitely added those up, well, probably added those up correctly. So that's using the formula that's on page 25 related to the Wilcoxon rank sign test of a half n plus 1 should be the total of the ranks. So now we are going to be using this U formula that I wrote down at the top. This is where we're actually getting our test statistics from. So the first U, let's call that UA, and the second one is going to be UB. Now the formula involves T and it also involves N. Well, NA is going to be the number of pieces of data that there were in A, which is 7. And NB is going to be the number of pieces of data that there are in B, which is 8. So for the first one, we're doing T, which is 47, minus NA, which is 7, times NA plus 1, so 7 plus 1, all over 2. For UB, we're going to be doing TB, which is 73, minus NB, which is 8, times NB plus 1, so 8 plus 1, over 2. Now we're going to put these into our calculator. So for UA, that gives us 47 minus 7 times 8 over 2, which gives us 19. And for UB, we get 73 minus 8 times 9 over 2, which gives us 37. And just as we have done in quite a lot of these hypothesis tests now, the smallest one of these is going to be our test statistic, which in this case is 19. So our test statistic is 19. Our critical value, so this is a one-tail hypothesis test at a 5% significance level. So if I just go back to my tables, so looking at the descriptions as to which one we should use, like I said, it was one tail 5%. So that's this top table here. And as you can see, we've got M and N. Now these are the different sizes. So in one group, we had 8 pieces of data. And in the other group, we had 7 pieces of data. So we look at where those two values cross, and that gives us a value of 13. Now it doesn't matter which way you do this, you could go 7 across and 8 down and you would still end up with the same critical value because the table is symmetrical. So that gives us a critical value of 13. And again, as the test statistic is bigger than the critical value, in the same way as we were talking about before, that means that the difference between these two U values isn't big enough to say that there is a difference, so we end up accepting H0 at a 5% significance level. There is insufficient evidence to suggest the average weight of a grapefruit from supermarket A is smaller than supermarket B. So I'd now like you to pause the video and give the Now You Try a go, just as we had with the Wilcoxon rank sign test and also Spearman's rank correlation coefficient. Anything that is the same number should also have the same rank, so this might involve adding ranks together and dividing by how many you are sharing them between. Please pause the video now and give the Now You Try question a go. So hopefully you paused the video and gave the Now You Try question a go. So here we have a French teacher has decided to try a new approach to getting his students to learn vocabulary. He selects 2 groups, each of 6 students of similar abilities. One group is left to learn their vocabulary in the usual way, but the other group is instructed in the new approach. The 2 groups are then given a test, and the number of words correctly remembered out of a list of 30 is given. So we can see the data for the usual way and the data for the new approach. Test the hypothesis that the new approach leads to higher success rate in learning French vocabulary. Use a 5% significance level. So this time we've got E to U and E to N, so our flicky N and U being less than N, where E to U is the population median number of words correctly remembered using the usual way, and E to N is the population median number of words correctly remembered using the new approach. As I said, it's Really good to make sure that you're writing those definitions down, making sure it's very clear which one stands for which one. And it also helps when you come to writing your conclusion. What was I actually talking about? What was this test actually about? Sometimes you can get bogged down performing this actual hypothesis test because there's quite a lot of different steps to it, and by the time you get to your conclusion it can end up being a little bit foggy what the test was actually about, when actually the conclusion is the most important part. So then we needed to rank our data as one big set. So 11 was the smallest, that got the rank of 1. Then 14 was 2, 15 was 3. Then there was 2 16s which share in the rank of 4 and 5, mean that they both get the rank 4.5. Then next there was 2 17s which get the rank 6 and 7, which means that they both get the rank 6.5. Then 18, 19, 24, 25 and then 29. Then we have to add those 2 rankings up separately. Remember, it's the rankings that you are adding up, which gives us 23.5 and 54.5 for TN. The number of pieces of data in U is 6 and the number of pieces of data in N is 6. So then we end up, when we're using our formula, remember it is given in the formula booklet on page 26, we get 23.5 minus 6 times 7 over 2, which gives us 2.5, and we end up with 54.5 minus 6 times 7 over 2, which gives us 33.5. Again, we choose the smallest of these two to be our test statistic, which is 2.5. The critical value we get from the formula booklet. Again, it's 1 tail 5%, and this time we have 6 in each group, so we're going across from 6 and down from 6, which gives us 7. So as the test statistic this time is smaller than the critical value, that means that there's a big enough difference between our two U values there to mean that there is a difference. So we end up rejecting H0 at a 5% significance level. There is sufficient evidence to suggest that the average number of words correctly remembered using the new approach is higher than using the usual way. So now we're going to have a look at how to perform a two-tail test using this. Again, it just depends on which table we end up having to look our critical value up and our hypothesis that changes. So here we have a cardiac consultant at a large hospital decides to measure the cholesterol levels of a sample of outpatients seen in her clinic. The results were, and there are our results. Using a Mann-Whitney U-test, remember that's just another name for the Wilcoxon rank sum, to test at a 5% significance level whether there is no difference between males and female cholesterol level. So this time we're going to have our H0 being eta M equals eta F, and our H1 is going to be eta M is not equal to eta F, where eta M means the population median cholesterol level of males, and similarly but for females for our other symbol, median cholesterol level of females. So now we need to rank our data as one big set of data. It's a little bit more difficult with these numbers here. Remember that you could use the sorting tool in the statistics mode just to re-show you where that is. If you typed all your data into your calculator, you go across to tool and then sort ask, it'll sort the values in that list into ascending order once you direct it to do that. I'm just going to do it here because it can be a bit confusing. You know what order they go in, but you're going to have to type them into your calculator, then sort them and then find them again, and sometimes that can add extra time onto the task. So the smallest one that we have is 1.5, that gets the rank 1. The next biggest one that we have is 1.7, that gets the rank 2. The next biggest one we have is 1.8, that gets the rank 3. Then the next biggest one we have is 1.9, that's going to get the rank 4. There's no more 1 points, so now looking through for 2 points. So the next biggest one is 2.1, which gives us 5. Then the next, looking for 3s, so 3.1 gives us 6, 3.7 gives us 7, 3.8 gives us 8, just having a quick double check I haven't missed any out there. Then 4.2 is going to be 9, 4.9 is going to be 10, 5.3 is going to be 11, 6.2 is the rank of 12. Then we have two 7.1s. They get the rank of 13 and 14, split between two of them, which means that they each get a rank of 13.5. So 13.5 for that 7.1 and 13.5 for that 7.1. Then 7.3 gets the rank of 15. 9.2 gets the rank of 16. 9.8 gets 17. 10 gets 18. 10.2 gets 19. 10.5 gets 20. And 10.9 gets 21. And then just double checking that we have numbered them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 11 pieces of data in the other, which do add up to 21. So now we need to get the total for the females and the total for the males. So remember that we add up the rankings. So we're going to have 11 plus 5 plus 8 plus 18 plus 2 plus 13.5 plus 17 plus 4 plus 6 plus 1. And that gives us 85.5. Then we have 15 plus 3 plus 10 plus 16 plus 13.5 plus 9 plus 19 plus 21 plus 7 plus 20 plus 12. And that gives us 145.5. In total, that's 85.5 plus 145.5. And it should add up to, there was 21 in total, so 21 times 22 divided by 2. So they do add up to the right amount. The number of pieces of data that we have for females is 10. The number of pieces of data that we have for males is 11. So now we are going to use our U formulas. So for UF, that's going to be 85.5 minus 10 times 11 over 2. And for UM, we are doing 145.5 minus 11 times 12 over 2. So 85.5 minus 10 times 11 over 2, which gives us 30.5, and 145.5 minus 11 times 12 over 2 gives us 79.5. So that means that our test statistic is 30.5. Our critical value this time is 2 tail at 5%, so we're using the bottom table. We have 11 in one group and 10 in the other, so that gives us a critical value of 27. So then, as the test statistic is bigger than the critical value, that means that there isn't a big enough difference, so we end up accepting H0 at a 5% significance level. There is insufficient evidence to suggest the average cholesterol level is not the same for males and females. And in a similar way to, again, thinking of binomial, normal, any hypothesis test where we have one tail and two tail, for the two tail version we are going to be saying not in our conclusion, because remember, in our written version of the conclusion we are referring to H1. I would now like you to pause the video and give the Now You Try question a go. So hopefully you paused the video and gave the Now You Try a go. So here we have a town fair and an archery competition for children aged 12 to 15. There were 12 entrants for the competition, 4 were girls and 8 were boys. Their overall scores at the end of the competition were, and we got the table of data there, at 5% significance level, use a suitable non-parametric test to determine whether there is any significant difference between the scores of boys and girls at archery. So because there are different sizes of samples for the girls and the boys, the only suitable non-parametric test that we've looked at is the Wilcoxon rank sum or a Mann-Whitney U test. Remember, that's the same test. So for our H0, we've got E to G equals E to B. H1, we've got E to G is not equal to E to B. And again, we have our definitions there. Population median score for girls at archery, population median score for boys at archery. Then we rank our data as one big set of data and add each of the rankings up separately, which gives us a total for the girls of 22.5 and a total for the boys of 55.5. The number of pieces of data that we have for girls is 4. The number of pieces of data we have for boys is 8. So then when we use our U formula, we're doing 22.5 minus 4 times 5 over 2, which gave us 12.5. And for UB, we're doing 55.5 minus 8 times 9 over 2, which gives us 19.5. So then our test statistic, the lowest of those two, is 12.5. Critical value, looking at the bottom table, 2 tail 5%, and this time we have 4 and 8, which gives us a critical value of 4. So as the test statistic is bigger than the critical value, we accept H0. At 5% significance level, there is insufficient evidence to suggest that the archery score is not the same for girls and boys. Thank you very much for listening.